So we will be continuing our discussion on this Bayesian decision theory or Bayesian inferencing. And in the last class, we discussed about the Bayesian network. And before that also, we considered the optimal decision making using Bayesian theory. Now, we will be further elaborating that concept in terms of in terms of losses and risks that is associated with any decision. So earlier in our discussion, we have considered only the probability of of classifications, and that means a kind of a strength to a class, and then that is weighted by your I should say by the corresponding decision process. Some kind of what I should say, that there is a policy which has been designed, some kind of functions we have defined, which will be expressing either the I should say gain or loss against that decision. So I think this is further elaborated here. So you consider you have a set of actions, and that is denoted by here with this symbol, say AI. That means ith action. So there is a set of actions. Now, each action is associated with the kind of say I should say the posterior probability of X of a class given that data. So here, let me elaborate it. Let me explain it. Say we consider, say the action is assign X to class Ci. So that is what is the action. That means assignment is an action, and you have, if there are say n classes, you have one of these possibilities. So there are n actions. So given a data, given an instance X, you would like to take one of these actions. Now, every action is associated with certain kind of loss. So the definition of this function, of this loss function in this case is given in this way. It's a kind of enumeration of losses for an action AI if X belongs to CK, which means actually suppose the instance belongs to class K, but for some reason you have considered the assignment to class I. Okay, so it's a general situation. It could be that it belongs to the class Ci, and also you are taking action AI, which means then this is given as LII. That is a theoretical representation of a loss when your actual class and your assignment they agree. Naturally, as you understand intuitively, that loss should be zero. At least it should be very small compared to all other kind of actions. But it may be also a zero. I mean, that is more natural. If you take a correct decision, you consider that there is no loss. So, but in a very general way, you have this kind of weightage, which shows that you are trying to bring a factor that not all kind of error is equally penalized. That means X may belong to some class, say 1, and assignment to other classes will have some varied losses. So it is possible in this general framework. In our previous examples, we have considered only binary situations. So either you have a loss or you do not have a loss. When it is a correct assignment, there is no loss, and for any other wrong assignment, there is an uniform loss that we have considered. So, but it is more general in this kind of framework. So now the question is that what is the expected risk for taking action AI? So that can be considered that, sorry, as you know that this is the risk, I should say, weighted by the posteriors. That means you can consider what is the probability of the class CK given X. And suppose you have taken an action AI. So for every, so the losses are given by AI, LIK in that case. So simply it is weighted sum of LIKs, where I is fixed. That means for AI only you are considering this expected risk, and the weights will be depending upon the posteriors of that class given that sample. Okay, so if your loss is if for the correct class assignment, naturally the loss will be very low, maybe 0. But then again, the posterior probability, if it is not high, then as you can see, that it has greater risk. So, so this is the kind of expression, as I was mentioning, that if I show you using, say this is the weight, right? And this weight is actually the posterior probability, and since sum of this posterior probability should be equal to 1 given any sample X, and if there are K classes, so sum of, I mean, if there are, say, N classes, right? Consider, say, there are N classes. I'm not sure. I have to check that what is the value of number of classes I have considered later on. But let us consider for this example, say there are classes starting from C1 to Cn. Okay. So what should be the sum of this posterior probability? What should be sum of, say, probability of Ck given X for all these classes? What should be it?
1.
Yeah, it should be equal to 1. Okay. So that's why now we call it, see, expectation, right? It's the same model. So every LIK has occurrence of LIK with this probability. So this is the probability model. So as if, so this is the expectation of the risk, expectation of the risk, or expected risk, or we can say expectation of loss also with respect to these observations X. So given this action AI, this is the expectation, expected risk. So suppose, so how many actions are possible here in this case, according to this particular framework? How many actions are possible? There are n assignments. Yeah, there are n assignments. So you get n such expected risk for each action, right? Then which one you should choose? Which action you should choose?
One with the minimum risk.
That's right. Exactly. One with the minimum risk, and that is what is that for optimal decision process, what we are saying under this Bayesian inferencing rule. So let us proceed. As you see that choose AI which minimizes this particular expected risk given that. So some of the examples, some of the illustrations could be that in a normal case, what we discussed earlier also, this is the usual loss model. So you can see that no, the loss is 0 if it's a correct assignment. That means your action has chosen the correct class. So your loss is 0, and all other losses, all other penalties, they are uniform and they are kept as 1. See in this model. Okay. So in this case, if I use the same expression, say this was the expected risk. Okay. So what should we, if you simplify it, what should be the value? What should we, how do you write it? Can you compute it and can you simplify this expression in terms of only posteriors?
So posterior distribution of correct class with respect to x.
Now I want mathematical expression. Say you have been given all these parameters, right? All this. So you have computed posteriors for all classes given x. That you can, suppose you have computed that using the procedures what we discussed earlier, and you have also given this particular loss model. So how can you express? Pardon?
1
So 1 minus
is TCI given x.
Said, as I have mentioned also, that sum of posteriors given that instance for all classes, that should be equal to 1. So we can write it like this. So you see that it is a normal case, what you have discussed. So, so minimization of risk means what? Maximization of, in this case, minimization of risk means you are trying to maximize the posterior. Okay, so you are choosing that class. You are choosing that, there you are choosing that action where it is minimizing the risk, which means you are choosing that class where it is maximizing it. So far, no, it looks very trivial and it looks equivalent. So what is the advantage of this kind of framework? That we will see in the next illustration. We can generalize this particular model further. Please mute your microphone. So let us consider some other in a generalized situation that see in the previous case I have mentioned also when you are taking this Bayesian inference that when you are choosing a decision, we have considered that action that for the class I will be choosing that class whose posterior is maximum out of all the classes. Now there finally, you know, if I just use that particular step computation, then we are not really bothering that what was your value of that posterior itself, how distinct it was, what was the next, I mean which class which has a very close posterior value. So that kind of things we have not judged. We have taken a very crisp decision. But in this model, now you can consider that your posterior also has to have certain strength. That means, suppose you have a very large number of class. If you have a very large number of class, the posteriors may be very low posteriors, but no, when you are choosing a maximum out of them, one of them will be maximum and you can choose them. I hope you got my problem. So posteriors could be very low, but still it is the maximum and you are choosing that class. Now that kind of scenario is not very desirable. So you should have at least certain strength in your posterior probability. So that is how you can consider in this decision-making process. You can take it in a very simple way. One thing you could have done that you just give a simple threshold, etc. But in this model, we will be showing how you can consider it. Suppose we consider an additional action. That means if you have, say, n classes, here capital K is the number of classes. Okay, capital K is the number of classes. So if you have, say, capital K classes, you had capital K number of actions. Now, additional action means suppose there is K plus 1th action. And this action means I'm not assigning any class. You understand? So it's a doubtful case. So it is better not to assign any class to it. So the loss function looks like this, that if I choose any action I, and if the true class is say K, then the loss would be 0. If I assign it to any other class, then there is a penalty 1. But if I do not assign, in spite of it being to a class, we know that it has to belong to some class. That is the kind of inductive assumption. Those are the inductive bias in our model, that we assume these many number of class only exist, and your sample belongs to one of them. So with that premise, you are developing this kind of theory here. But no, in the doubtful case, what you do not assign. You know that it has to be assigned. There is some class to which this sample belongs, but you are not sure. That's why you are not taking any decision. Now, for that, you have a loss. But since you are avoiding the risk of misclassification, this loss may be less than 1. I mean, it's lambda. You could have also put it greater than 1. In that case, no, it does not have much meaning in this framework. We'll see that later on also. But suppose these are the values. Another additional parameter in your loss model, lambda, which is the penalty due to not assignment of any class to an instance. That's a separate penalty. So in that case, as you can see that if you consider any action AI, so as we have computed earlier also, it would be 1 minus probability of Ci given X. If I is not the K plus 1th action. For any I, that means for any other action except the last action, last additional action, K plus 1th action, the expected risk is the same. Do you agree? Okay. And if I take, yeah.
Is it like whenever we're not making any classification decision, then I mean we're not making any particular decision about which class the data belongs to, then we are assigning a loss function lambda. If we are misclassifying, then 0, and correct classification we are assigning 1.
No, misclassification is 1, loss, it's a loss, and correct classification is 0.
Yeah, misclassification is 1 and correct classification is 0.
Exactly.
Okay.
Exactly. So that is how it is computed. You see that you have to compute also risk of this additional action. Earlier you have computed risk of all the actions which correspond to the assignment to one of these classes, and then you also consider another action not assignment. So then this risk is a constant risk, right? For this action, it is constant. So now you see that if I apply the this minimization of risk rule, so optimum classification rule, so you have this, no? That which means if your posterior is maximum, and also if your posterior is greater than 1 minus lambda, then you should accept it. Otherwise, you should reject it. Is it okay? It is greater than 1 minus lambda, isn't it? Fine. Any confusion? So this is how you are implementing this particular policy that your posterior should have sufficient strength. Right. So as I was mentioning that it is meaningful if lambda ranges between say 0 to 1, and if lambda is 0, then what it means that you are always rejecting it. That means posterior has to be greater than 1, which is not possible. So if you choose the value of lambda is 0, then you are always rejecting it. If you choose the value of lambda equal to 1 once again, then you are always accepting it. Now, this is a scenario. So naturally, lambda should be between 0 to 1, then it is meaningful, and then you can put that kind of conditions. So value of lambda should be low, as you can see that to give it a considerable strength, value of lambda should be low on the lower side. Now this particular decision making process, this optimal decision making process also can be generalized in terms of utility theory also. So instead of loss, we will be considering utility. It is the same framework, only the terms are different, and instead of minimization, now you do the maximization. You can see that exactly the same framework, only it is being shown in a different way. Instead of loss, we have utilities, and you are computing expected utility in the same way, and here you are choosing the maximum out of all actions. Now this is about this optimal decision making process using Bayesian inference. I will discuss a slightly, I should say, a bit different topic, which is not a directly, I should say, which is not a direct application of Bayesian inference, but which is closely related with it. You can see that, and that's why I'm putting it into the same, under the same consideration, and it is very important. It's a very important task, very interesting task that you will see in many cases. We consider, we try to find our association rules. Now, the background is that you have seen, many of you are now acquainted with this kind of recommendation system. So in the online purchase, whenever you buy some item, you will find there are a lot of recommendations, a lot of suggestions. So by considering the history of procurements of different customers, the corresponding retailer, they give you a lot of suggestions to the prospective buyers with the hope that if you buy that item, you may be interested on buying these items also. And it has been, that in the business, it has a great importance nowadays. So we call it a recommendation system. And in the core of the recommendation system, this principle is used. That means you have to find out the association between events. Suppose the event is that you are buying a purchase of, you are buying an item X. So how it is associated with the procurement of another item, say Y. So we consider to find out that kind of relationships between different tasks or events. So let us consider a very general representation of that particular fact in this form, which is very familiar to all of you. That's an implication. I hope you immediately have recognized that this is what is meant by association, that X, if X and then Y. So the event X implies that Y also takes place, right? And this implications, we are trying to, what is our problem statement? Problem statement is that given the probability distributions of X, Y, maybe joint distributions also, given those all those records, I mean, basically the history of the events of X and Y, they are joint occurrences, they are independent occurrences, whatever form the histories are available, and then you have to you have to check, you have to find out whether one of them is associated with the other, whether implications are there, whether X implies Y or the other way, Y implies X. So, so this kind of thing we are trying to find out. And there is a technical term, as we have also mentioned in the case of this rule base, when you have discussed about decision tree and formation of rules. You can see also it's nothing but you are trying to find out some rules, and you know that the antecedent part, that is the conditional part of if then kind of logic. So if the antecedent is true, then the consequent is true. So you are considering that kind of thing. So as I was telling you, the example is that basket analysis for dependency on procurement of items X and Y. This I started with this example. Now, how do you proceed? What are the approaches? There could be various approaches. So I will be just illustrating some approaches which are discussed in that book, Alpeidin's book. So you can check that book. I mean, the chapter I have already mentioned in the beginning. You can find out the chapter name. I just right now I do not remember it. So check that part, please. So from that book, I'll be discussing this one. But you don't take it that this is the only way these associations are found out. I mean, there are many other techniques. They are possible. It's a very widely researched topic. So 3 useful measures from the probabilistic sense. That is how we are relating with this our particular Bayesian inference part. We'll see that one of the thing is that we should consider to compute the joint probability distribution of these 2 events. That means there has to be some basis that they have some relation. So if they don't occur jointly, in a significantly their joint occurrence is not observed, so you may not be interested. So we call it support of these 2 events XY. That is the functional term. That is, we compute support of 2 events XY, which means actually we are computing the joint probability. So support is proportional to this, which means that you can compute in this way in a very, that means the definition is direct definition, that number of customers bought X and Y. So our discussion is with respect to this basket analysis. So number of customers bought X and Y divided by number of total customers. I should say it's not number of total customers. It should be number of procurements, total procurements. Yeah, it should be number of total procurements. X and Y. XY could be any value. 10X and Y, and see, it should be over that. This definition has some problem is with this definition. It should be computing probability of joint probability of X and Y. We'll see with respect to a particular example. Maybe example I have not given here. We'll come to that. This definition, I think I have taken it from Alpeidin's book, but now I'm finding some problem maybe there. But we have to compute this joint probability distribution of this of the item sets X and Y. Then the confidence, which is given by this particular, which is expressed by this one, that probability of Y given X, and as you know, that conditional probability that can be computed once again. That this is related with the probability of XY divided by probability of X. So X and Y, they are, as you understand, they are random variables here, and given those values over the XY values, only you are observing. So joint distribution. So number of total customers should be modified to that. What is the total number of occurrences, joint occurrences of considering all possible pairing values of x and y, what is the total number of occurrences in your observation set. And given a particular pair of values of x and y, what is the numerator would be that when you are computing probability of x, y, that's joint distribution, right? So given that, and given an item x, you can also find out what is the probability of x, and then you can compute this probability of y given x using this relationship. This is that the corresponding. It is also expressing the Bayesian relation, as you can see, the same conditional probability distribution. So here it is once again number of customers bought x and y divided by number of customers of x. I think they're equating any particular procurement with that event, they're equating with the number of customers. And then the other measure, which tries to see that how these two events, x and y, they are independent. As you can see that the numerator is the joint probability of x and y, and the denominator is product of them. Now, if x and y are independent, you know that it should be same as the denominator. That means probability of xy should be equal to probability of x into probability of y. So value of lift xy should be equal to 1 when they are independent. But since you are trying to find out your interest is to find out the association. So if there is any association, you expect these values should deviate from 1. Either it should be in the higher side or it should be in the lower side with respect to 1. Okay. So these are the three useful measures by which we can design certain algorithms, and we'll see later on to find the association. So these are the implications of these three measures. One is that the confidence, which is the probability of y given x, it should be very high. It should be close to 1. In fact, it should be significantly higher than probability of y. So normally probability of y may not occur so frequently, but whenever x occurs, you are finding in a significant proportion y will occur out of them. You know that probability of y given x is defined as, once again, the joint probability of xy divided by probability of x. So out of all x occurrences of x, the number of times the same y should occur, that should be significantly high. That is how the confidence, and it indicates the strength of that assertion. And the support shows statistical significance, which means it's they should occur in a considerable number. So if you do not have if you do not have that many occurrences, then no, you are not much interested also to find out the association. That is the idea here in this context. And as I mentioned that for association, this ratio should be other than close to 1, which means it should deviate from 1. And this is the kind of implications that if lift is greater than 1, most likely x makes y, else less than 1 means y makes x. That means a kind of a causality it is trying to indicate, though association does not mean causality, but it throws some indications in that direction. So there is an algorithm which is called a priori algorithm, and it is quite old. In 1996, this algorithm was reported, and this algorithm is widely used in the database data mining areas. So I'll be just discussing a brief outline of this particular approach. And as you see that what it tries to get, and it is trying to consider from the database's perspective that functional dependencies. If you are aware of database design, you know that we define this particular property of among the attributes, that functional dependencies of the attribute sets. So that is what is the associations. That is what we are trying to find out in this context. So, and it is considering also that the more than two variables. So that X is not a single attribute; it could be a combination of attributes. There are two steps in this algorithm. First, it finds the frequent item sets, which means that we are interested to look at those support. We are trying to find out the combinations where there is I should say, which occur in significantly with respect to occurrences of other combinations. So we try to find out frequent item sets. That means those which have enough support, and then which means now for each item sets which are frequent. So you have identified certain a combination of item sets. There now you try to find out that a part of it is implying the other part. So that is the kind of relationships association you are trying to find out. That means a part of it will be in the antecedent part, and the other part will be in the consequent part. So you have to convert them into rules, and which means that as I was mentioning, that you split them into two, so that one part is expressed as an antecedent and the other part as consequent, and you are checking whether it has enough confidence. So you are proposing. So the first step, you are trying to form certain hypothesis that possibly this is the combination where we are likely to get some associations within these attribute sets. In the second, I should say not hypothesis, rather I should say in the first you are trying to get a set of attributes where there is a possibility to find out some association rule. And in the second step, you are forming hypotheses from those possibilities. So you are forming hypotheses, and each hypothesis is being, I should say, checked by computing the corresponding what I call strength, strength or evidence, whatever. That means that implication part. So that you are computing probability of consequent given the antecedent, right? So that is what you will be computing, and if it is significantly high, then you should take them. So this is the way it goes, that you find the frequent item sets, that is those which have enough support, and for that what you can do that, because this combination could be exponentially explosive. This combination, the number could be exponentially, as you say, it's an exponentially explosive number. So what you can do that you can use some greedy approach once again. So the greedy approach says that first start with a small set of combinations. That means start with say 2 items, and if you find frequent occurrences of these 2 items, then you try to increase the set with another additional item. Only for those 2 items where it is it has occurred in a significant number of times, then you are extending them. Otherwise, those items which are not occurring significantly, you just discard them. So in this, you are eliminating many possibilities in that combination from the beginning in a greedy kind of approach, and you proceed like this. So cardinality, and then you remove supersets in the combinations which are not in the list of lower cardinality sets. So which means that if X is not frequent, do not search for any combination with X. Okay, it starts with 1 item. It is not only starting with 2 items. It starts with 1 item, and you go through these things. And if you have in total n item sets, it requires n plus 1 passes. So this step, it requires n plus 1 passes for searching largest n item set together. not total, I mean largest in item set. That means you may have more number of items, but you are interested only you. That's the parameter that you will be considering to check for association only with this combination of at most n items. Now, as I was mentioning that this is a second step where you will be searching for the strength of these implications or evidences. So that is confidence, right? That is the term we have used. So we can convert them into rules, and then you compute its confidence. So we can do in this way that you can split the items. So what you do in the beginning, because you would like to see whether the as you know from the functional dependencies, suppose x is say z is functionally dependent on x. So in the database perspective also, so given any other attribute set with x, still you will find that z will be functionally dependent. That means x comma y, if it is functionally determining, is it true? X comma y. No, that is not true. Sorry. So let us proceed. That is not true. So it has to be both. It should be functionally dependent on both x and y. So that is why we are checking it first. We are checking it first, and then if it is not true, then we will be discarding y. Suppose we will be checking x determines z or y determines z. So that's why we start with the larger number of combinations in the antecedent part. So if you have say k items, so you consider k minus 1 items in the antecedent and 1 item in consequent, and remove those rules which fail the test of confidence. And so you can keep only those rules. So we are not really going to check the lower cardinality things only. Only we are trying to consider this k item sets. So you may start with the k can vary. So in every pass you reduce antecedent part and increase consequent part. So you are reducing this, and also you are increasing the consequent part, which means you are also trying to see that those because it is easy to check in the consequent part independently. You can check it. So with the antecedent independently, you can check occurrences of consequent parts. Each item sets in the consequent part. So rules with larger consequent part that are more useful. So that is again from the databases point of view. That if you can produce that certain event x is implying a set of other item sets. So procurement of x is implying a larger set of item sets. So that becomes useful in terms of this association. So a few considerations here, that as I was mentioning, that association is not really indicating causality, and also there may be some hidden variables which are not identified. So it is merely reflects. So that's why causality you cannot say that which is the cause. You observe that these two has a more frequent occurrences, and if something happens, of course the other one happens, but whether it's a cause you cannot say. For example, there's a nice example is given in that book itself. Say you have an association among these items, say diapers, baby food, and milk. Now this may be established, but the hidden variable is that that baby at home. So which is not which may be the reason for all these events to take place. So we really cannot say that buying diaper and buying is causing buying milk, or buying milk is causing buying diaper. So that kind of simplistic inference you should not carry out. So with this, let me summarize this particular topic on Bayesian inference, what we discussed under this topic, like no, as we see that we have computed this Bayesian inference means primarily that no, you have to compute a posterior probability of the with respect to classification. This is what posterior probability of classification of classific classes given a particular instance, and you can make also optimal decision making. Instead of a crisp decision on a particular class, you can make in some and weighted. No, you can use a weighted policy for taking a decision, like modeling risk or utility, as we have seen. And we have also discussed. We will later on. This particular thing will be further explained that Bayesian inference can be also brought under the framework of discriminant functions in a general mathematical model where classifiers are also specified, and it is useful in establishing association among variables. We have seen in what way it is. It is not directly, you are computing posteriors. It is not like that, but it has implications to that. So, where you are computing the probabilities of several probabilities, I should say. So, it's a probabilistic approach of finding associations, and where this Bayes theory has its role to play. So, the rules there, the last part, that with high support and confidence and if not around 1, so that should be considered for the association. So with this, let me conclude this particular topic.